All right, everyone, looks like we're almost ready to get started. And today we're going to have a guest lecturer to talk about cloud computing. So, Varun.
Thank you. Hi, everyone. We had a little bit of delay trying to get the projector stuff set up, but now we're through. And I'm Shivram. I'm a PhD student in the AMP lab at UC Berkeley. And today I'm going to be talking about cloud computing and big data and how it relates to the kind of stuff that we're looking at in this course, parallel computing. Before we start, I'd just like to thank Professor Demel for giving me this opportunity to give this lecture. So I think most of you in this room would have heard these buzzwords of like big data and cloud computing. They're all over the place these days, and it's kind of hard to put your finger on what do they exactly mean. And this is not just in the computer science or the IT field that you see this. Even magazines like The Economist and like Nature, they're running these like big things on big data. So what I'm going to try to do in this talk is to talk about two aspects of this cloud computing and big data stuff. The first thing I'm going to try to do is talk about the hardware and the kind of machines that are powering the applications that are used either in cloud computing or to process large amounts of data. And I'm going to try to compare this to how it relates to stuff like Hopper or the other supercomputers that we've seen so far in this course. The second thing I'm going to try to do is to look at the software side of it and like look at what are the programming models, what are the software stack which are used in these settings, and again try to do a compare and contrast with things like MPI that we've looked at or like UPC that we've looked at and see why they're different or how they're different and so on, right? So to start the story, we go back in time a little bit, more specifically to around like 1997 to a small like lab in Stanford. And I guess most of you can identify this, but this is like where the first Google set of machines were hosted when they were building their first prototype, right? This is kind of significant because Google was one of the first companies which ran into this problem of how do I serve and like how do I process large amounts of data. So I found this really nice excerpt in one of their first papers that they wrote. This is from 1999, where Larry and Sergey wrote this paper called The Anatomy of a Large-Scale Hypertextual Search Engine. And there's a quote here which says that storage space is like this really critical factor. And what's really important is that we must be able to process hundreds of gigabytes of data and serve them efficiently. Now, most of your laptops have more than hundreds of gigabytes of data, and like you can probably serve it pretty efficiently, but it's a pretty big deal at that time. But more than the actual number, this insight that the large amounts of data is going to be the key problem was, I think, was one of the earliest insights that Google had. So what did Larry and Sergey do when they ran into this problem? They do what most people would do. They bought a bunch of machines and tried to put it all together and make it work. They said, OK, I don't have disk space in one machine, so I'm just going to use multiple machines and make my own cluster to try and like do this. But there were some significant characteristics about this cluster. So the first thing was, they were just getting out of graduate school and starting a new company. So what they did was they just went to the nearby store, let's say Fry's or something, and bought a bunch of PCs and connected them together. So these ended up being like commodity machines that anybody could buy off the shelf, right? The second thing was data was their problem, and specifically storing all this data was a huge problem. So they attached a large number of disks to each machine, like how much ever they could with the amount of money that they had. And the last thing was that they just connected them using any sort of network connections that they could get. These were mostly like the default NIC cards that you see in your desktop or your laptop computers and so on, like nothing fancy, no Tori or like no 3D torus and stuff of that sort, right? The key idea here was that they wanted to make it work with as little money spent as possible. So the cost efficiency was like this great problem even from like the first day. But so this was in 2001, this photo, which looks like a cluster of around like 8 or 16 such machines. And as we all know, the amount of data has grown, right? We no longer have several hundred gigabytes of data. We have probably tens of petabytes of data, right? Google doesn't index like hundreds of thousands of pages, but it's gone into billions or trillions of pages now, right? And also, we've had this trend of more and more data sources popping up. There's like this Human Genome Project, which around the same time was like we sequenced the first genome, which was like around 1999 or 2000. And now there are like 1,000 genomes being sequenced, thousands of genomes sequenced every day. And each of these genomes are like terabytes in size, right? Daily logs in something like Facebook, like just like access logs of billions of people like accessing the website is like 60 terabytes a day or something. And this curve is growing. There's like many versions of this curve. This is from an IDC report, which just shows that this is the Moore's law curve, which most of us are familiar with, of how processing speeds double every year and a half. But data, it looks like, is on a steeper slope. So in some sense, we're like getting much more data than we can like process. Like we just don't have enough like computing power to like process so much data, right? So, and as a result of that, what's happened is what looked like that small like table with like 4 PCs has become something like this, you know. So this is 3 of Google's data centers, sort of like co-located with each other in a place up north in like Oregon. And what it shows is that each of these data centers that you see, which is at a very high level, is like the size of a football field. So it's like huge and gigantic, and they're like tens of thousands of machines which are like interconnected, all of which is like storing all this data and processing all your search queries and so on and so forth. And this is just one site. Companies have like tens or like, it's confidential, so they don't exactly release how many such data centers they have, but they're spread out all over the world, like in the East Coast, the West Coast, Europe, you name it, right? So data centers have evolved a lot, and it's very interesting to study how have the hardware characteristics of these things changed, right? From like the earliest machines that we saw. So one thing that's happened is that we have petabytes of data now. How are we going to store it? So the simple solution is we get like tens of thousands of machines, split it up, store it on all of them, right? Seems like a good idea. But there's a bigger problem. If you can store it, how are you going to access all that data? You need bandwidth to access all that data, right? It's a very critical problem, especially if you want to process large amounts of data in a short amount of time. Bandwidth becomes the bottleneck most often. So the trick they use here is you attach a large number of disks. So each disk is, let's say, around 100 megabytes per second or something like that. You attach 24 disks per machine, you get like really high bandwidth. You get like 24 times that bandwidth. But bandwidth is no good if you're a user who's like waiting for a search result. Research has shown that if anything takes like 100 milliseconds longer than what it's expected to take, the number of clicks and like number of pages people visit like sharply drops off. So latency is another critical factor. And the way people have reacted to this is that they throw large amounts of memory to cache data in between. So you don't hit the disk on every request, and most of the requests are served from cache. And as a result, there's been like growing cache sizes, and each machine now has like 256 gigabytes of RAM, just so you can cache almost all of the data that's coming through. So this is a very interesting trend, and the final note is that when you have tens of thousands of machines, the interconnect starts mattering, right? If you have a small rack in a small room, you can connect them however you want, and you're probably going to be still okay. So data center networking has become like a really important and big problem in the last 3 or 4 years. The initial sort of set of like assumptions people made was to use like a tree topology. We saw this like a couple of lectures back of how a tree topology works. But the tree topology has a bunch of oversubscribed links. So you don't have this notion that any machine can talk to any other machine at like high speed. So more recent research have proposed things like using a factory and other techniques like B-cube and stuff of that sort to get this idea of what is a full bisection bandwidth. The basic intuition here is that you want any machine to be able to talk to any other machine at like full network speed. And one way to do that is you keep doubling the amount of bandwidth at like every height as you go up in a level of the tree. So you have like 4 nodes up here in this sort of subtree, and there are like 4 links which come down from the root of that tree, right? So all of this work is being done so that we are able to organize and like process these large amounts of data being stored in these data centers. So extending this, where is this all going, right? I mean, so we've come a really long way from like 2001 to these giant football field-sized data centers. But what is the trend that we're seeing here? So I think the major trends that are seen in data center design today is still sort of retaining the same aspects that were true in like 2001. The first trend is that of like cost efficiency. Is like how can you reduce the amount of money that you use to build a data center and maintain the data center. Maintenance is like a huge cost when you're running like such large amounts of machines in it. The other important factor is this thing called PUE, or the power usage effectiveness. And the insight here is that when you run tens of thousands of machines, the amount of power usage that these data centers have is like megawatts in size, you know. So one of the aspects that I'm not sure if it was clear is that they tend to build these data centers close to power sources. So the one in Oregon has like a hydroelectric dam like pretty close to it, because there's like this huge power consumption that you need for each of these data centers. So this power usage effectiveness is this great effort to make sure that you use every watt of power as efficiently as possible. So this requires like redesigning machines, redesigning software, redesigning hardware, and all of things like that. And finally, there are efforts to go to a custom machine design. And what I mean by this is that exploring how many disks can you put in, what's the right number, like how is the interconnect supposed to look, how many machines in a rack, you know. There's like a variety of different techniques people are trying out to sort of build like the ideal data center model. This whole effort is sort of really young. Whenever we talk about things like MPI, or Professor Demel introduced other things like UPC and so on, they're like standards. They're like organizations which are looking at things and so on, right? But this is a pretty nascent area, like the whole area of building data centers and so on. One of the first efforts towards standardizing things is this thing called the Open Compute Platform, which was sort of put out by Facebook as one of like the founding members. There are a bunch of other companies which are in it now, and they're trying to come up with these blueprints of how to build a data center. Because so far it's been a very ad hoc process of growth in trying to design these things. So this was all entertaining, but I promised to tell you about cloud computing while I've talked to you about data centers for like so long. What's like the bridge between these two? So the bridge between these two is sort of like an interesting thing to study, is that what people realize is when you have these large amounts of data centers, like huge amounts of computing power available, you can sort of treat computing power like a utility, like we treat electricity or like water, you know, as like this centralized utility that anybody can get access to. People saw this early on. This is a paper from a bunch of folks at Berkeley. You might identify a bunch of professors there, called Above the Clouds, a Berkeley view of cloud computing. This was sort of a vision paper that they wrote when they started this effort called the RAD Lab, which was a reliable and distributed systems laboratory. And one of the excerpts from that paper is that data centers can sort of power this long-held dream of computing as a utility, right? So there's this dream that you can get computing resources whenever you want at whatever granularity you want, and you can just pay how much ever you use, right? And data centers sort of enable that dream to come true in this setting. So it has sort of come true. From around mid-2006, EC2, which was an effort by Amazon, this took off, and what it basically did was it provided users the ability to rent virtual machines in the cloud, and you could like pay how much ever hours that you use your virtual machine for, and you were only charged for that. It also had this interesting effect of you could on demand increase the number of machines you're using and decrease it. So you have this flexibility of like, if you get more traffic or if you have more computation to do, you can get more machines. But if you're done with it, you can shut them down and you don't need to pay for them anymore. And lastly, there's this very interesting model called the spot pricing model, where there are a bunch of extra machines that are lying around, and what Amazon does is that it offers sort of a bidding model on these machines. So you can bid for like 20 cents an hour, and if somebody else bids higher than you, they get the machine. But if you win the bidding war, then you get the machine. So there are a lot of economic sort of like problems coming up in how do we use computing as such. So just to give you a flavor of what this looks like, this is some numbers I just pulled up yesterday. Amazon offers a large number of instances. I just pulled up numbers in different ends of the spectrum. The smallest of them is like this T1 micro, where you have like half a gig of memory. It's this like really tiny slice of computing instance, but it's like 2 cents an hour. So it's like really cheap for you if you want to just get a computer and like do something, you know. There's no upfront cost for you to pay. This is a pretty big deal, especially if you're like starting companies, or if you just like as a student you want to like use some computing resources, right? But there are other bigger machines. The most common middle range one is like this M1.extra large type, where you have around 15 gigs of RAM. This is kind of like your desktop machine that you would have, right? And it costs about like $50 an hour to like rent this thing. So you can imagine renting 5 of these or 10 of these to run some experiments and like let's say shut it down. It costs like $5 if you use like 10 of them for an hour. But they have also done this thing of giving you access to even large machines like the CC2.8 extra large at the bottom, which has around 60 gigs of RAM and an Intel Xeon processor beneath it. One funny thing which I should explain is this compute units going on out here in the middle column. And they're in this unit called ECU. The problem here is that Amazon keeps refreshing its hardware. So the processors actually keep changing, but they want to offer something consistent to the users, right? So they came up with this thing where in 2007 they said, we have a Xeon at this point, and we're going to call whatever the Xeon is as one compute unit. So as they refresh processors, they just keep giving it in multiples of these Xeon machines that were from 2007. It's sort of hard to understand what's going on with this, but the basic notion is that this is like 4 times more powerful than the T1 micro or something of that sort. It's an approximation, you know. There's one more thing I need to add is that most of these machines are virtual machines, so you don't actually know what's the hardware running beneath it. They use Zen as their virtualization medium, which is something you guys might have heard of. And what it does is that one of the good things is it gives you this nice thing where you can run whatever operating system you want and configure it however you want. But on the flip side, for doing really high performance things, like for example, in the first homework, we looked at cache sizes of like the process, right? You have no idea what the cache size is, for example, because you're looking at this virtualized machine and you have no idea what the cache size is inside the VM. So there's some pros and cons towards using these kind of virtual machines. So let's put it all together. We promised to look at this Hopper versus a data center kind of comparison. I should add some disclaimers that, like I said earlier, these data centers are sort of confidential information that no company tries to reveal. So the numbers that I pulled up are from recommended configurations that vendors usually suggest. So they're all approximations. You should take them with a pinch of salt. On the other hand, Hopper's numbers are very well described if you go to the NERSC website. So I just pulled them out of that. And this is sort of a high-level comparison. So the nodes, I think, are orders of thousands in both of them. And scale is something that grows. 2 years from now, it may be tens of thousands. Who knows, right? Hopper does have more cores per node. So each of them are like these 2 AMD Magni core CPUs with around 24 cores per node. On the other hand, these typical data center machines have fewer cores. The Cloudera suggested one from this blog post suggests having 2 6-core CPUs, which is around half of what Hopper's number of cores are. The memory and the storage capacity are typically larger. This is kind of motivated from what I showed you earlier of having bandwidth and caches and things of that sort. So typically each node has around 48 to 128 gigabytes of RAM, and this 120 to 420 petabytes of memory of storage is across thousands of nodes that I'm put up here. Hopper, on the other hand, has around 4 petabytes of scratch space where you can store stuff, but this is not the primary sort of focus of what Hopper was built for. And lastly, this interconnect is kind of an interesting thing. The 3D torus architecture that Hopper has I did a conversion from gigabytes per second, but it's around 66 gigabits per second, which is a really fast interconnect if you think about it. Even the state-of-the-art data centers probably have 10 gigabits per second full bisection, even if you throw a lot of money at it. So to just at a very high level, what you see is that there's a focus on storage as opposed to flops in these data center architectures. And so the technique is to scale out using commodity components, like adding more disks and adding more machines to your cluster. And finally, these things sort of in combination enable this pay-as-you-go model. So this sort of summarizes how the hardware looks in one of these settings. So with this, let's switch to the second part, which is to talk about the software stack. From the first part, what we've seen is that, we have this great data center. It has petabytes of storage, gigabytes of RAM. We're good, right? I mean, everything is perfect. World is beautiful. Well, often not, This is news reports from a bunch of different sources of problems that data centers can run into. The first one there is this outage in Dublin due to a lightning strike, which knocked off Amazon and Microsoft data centers. But it's not just Amazon, Microsoft. Gmail went down a few months back due to a data center outage. And it also affects things like EC2. There are these service disruptions that you see, and you get these things because things fail when you run them at scale. And these are not isolated events. This is from a slide from Jeff Dean at Google, and he sort of estimates the number of outages or number of failures that happen when you first bring up a data center. The interesting numbers here are things like, without warning, 500 to 1,000 machines will disappear and take 6 hours to come back. The reason for this is like some power unit somewhere in the data center fail, right? There are also disks which fail, like thousands of hard drives which fail, because you bought so many of them. If there's a probability of failure that one fails is like 1 in 1,000, once you have tens of thousands of them, something is going to keep failing, right? Like the math works towards that. There are also network maintenances, router overloads, you name it, and the number of failure modes is just too many to even list in a slide like this. This is even discounting natural disasters like earthquakes, lightning strikes, and like so on and so forth. So the biggest challenge is sort of, now we have these set of machines which are sort of unreliable in their storage stack, in their like compute stack and so on. How are we going to program this thing, right? How are we going to write any code and get any work done if we don't know which machines are going to be up and like which machines are going to be down and so on? So in some sense, what has happened is by choosing these commodity components, we've made the hardware's life sort of simpler, or the hardware designer or the architect's life a little simpler, but the software has gotten more complex because it needs to handle all these sort of uncertainties that exist in the hardware, right? So we've looked at different programming models so far in this course. The most prominent one we looked at was MPI, or which is this message passing model, where you have a bunch of processes which can send fine-grained messages and compute in parallel on a large number of machines, right? But it's kind of difficult to deal with things like failures and to deal with things like which disks are you reading data from in such a model. And the intuition here is that because in the MPI model, you are mostly controlling most of the code that's written, it's kind of hard to reason about what happens when one of the processes fail. Like, does it restart? Like, at what point does it restart, right? What happened to all the messages that you had sent and received from it, right? It gets complicated and gets hard to reason about for the programmer when you're dealing with such things. On the other hand, there are these data parallel models, which have actually been studied in literature for a long time, which have a much more narrower programming interface. They're more descriptive in the sense that they sort of describe what you want to do to the data, not how you do them. So it's less imperative where you exactly list out what instructions or like what lines of code are executed. But when you have a more restricted programming model, you can do things like you can handle failure, or you can handle machines which are behaving badly and like do things. So one way to describe it is that the data parallel model, it doesn't actually say this is the program you want to run. It says here's the operation that I want to do on my data set. Do it however you want to do it, right? So it sort of describes what needs to happen. More significantly, it doesn't actually care where it runs, because you've just described computation and you've left the freedom for like an execution layer to figure out where to run this thing. And also, it in fact tells you that if you want to retry this in like a bunch of machines, or if it fails, you want to restart it, do anything you want with it, right? So we've sort of imposed a lot of restrictions on the type of code you can write, but you get a lot of free things in return for it. And the free things are things like handling failures and so on, right? And one of the biggest incarnations of this programming model is the MapReduce software engine. This has become pretty popular in the last decade or so, but the first time this was introduced was in around 2004, when two people at Google, Jeff Dean and Sanjay Gemawat, they wrote this paper which just said MapReduce, a simplified data processing model on large clusters. Their basic motivation was to build a search index for Google and to generate page rank values for the large number of web pages that they had. And they were having a hard time trying to do it with traditional programming models. So they sort of came up with this simplified model where they could retry some of these tasks and automatically handle failures and so on. People immediately realized this was a good idea. So a bunch of folks at Yahoo and Facebook sat together and they came up with this open source version of MapReduce called Hadoop. And Hadoop has taken off a lot. There are a bunch of companies which are contributing to it. It's installed in a large number of places, academic places, industry, enterprises, and so on. I think even Hopper probably has a Hadoop option to run like some Hadoop jobs on it right now. And it's been scaled at places like Yahoo and Facebook to like 40,000 nodes to handle like 50 petabytes of data and so on. So there's a large scale effort behind Hadoop in terms of engineering, in terms of ops, and the ecosystem is sort of growing around it. So in the next few slides, I'll give you a sort of high-level flavor of how the MapReduce programming model works and try to use a few examples to explain why it works and how is it effective. The basic idea in this model is that we have a particular data type that we work with. And the data type that they choose is this one where you have a series of records in your input. Let's say it's like a file. You have a bunch of lines in the file or something like that. And each line can contain of a key and a value, right? So in some sense, this is sort of like a database model where you have a tabular data form where you have a list of keys and a list of values associated in every record. So the user pretty much writes two functions, a map function and a reduce function, sort of where the name comes from. And what this does is that the map function takes in a key and a value from the input and emits another list of keys and values as intermediate data. So this inter here refers to intermediate data. And this is applied on every key value of the input by the engine, right? So you just write this one function and it takes care of it. Now on the other hand, what the reduce function does is that it takes all of the values associated with the key in this intermediate output and it aggregates them to produce some output data out of it, right? So this goes from key, list of intermediate values to a list of key and value outputs. So it's a pretty simple interface, and you just need to write these two functions as a part of the interface. So let's take an example, and this is the most commonly used example when anybody introduces MapReduce. So let's start from here, which is this example of word count. A couple of classes back, we saw a histogram example in the UPC programming model, which is also around the same lines. So what this is trying to do is you have a file with a large number of lines in it, and you want to count how many times each word occurs in the file. Right? It's quite a simple task. And what you need to do as a programmer is write these two functions called mapper and reducer, and this is Python syntax that's used out here. And what it does is it just looks at each line, and for every word, it outputs word, comma, 1, which is like I've seen this word once, right? And the output function here is again, a key, comma, value. Right? Now what the reducer sees is that for every key in the intermediate data, it sees all of the values in it. So what does that mean? What that means is that if you have a word occurring like in different places in the document, you get both of its values as a list as an input to the reducer. So if you want to just count the number of times the word occurs, you just sum up all of the values that you see. In some sense, you're summing up the number of ones that you've emitted in the first space. Right? So conceptually, this is pretty simple. How does this get executed in a large setting? Right? So here I have a document which has 3 fragments, or like 3 sentences, you can say. And there are 3 map tasks which are going to be launched to handle these 3 fragments. And every map task splits it. So you do things like the word the is emitted once, and the word quick is emitted once, and brown, comma 1, and fox, comma 1. And this is repeated for each of these documents. Now, there's an intermediate phase here that I didn't describe to you so far, which is called this shuffle and sort phase. And what the shuffle and sort phase does is that it makes sure that all of the values belonging to the same key reach the same reducer. Right? So for example, we have the word fox here appearing in the second document and also in the first document. Right? We want the values for fox to come to the same place so that we can add them up together. So this is handled automatically by the framework. The programmer doesn't need to do anything about it, but the shuffle basically does a hash partitioning of all of the keys and sends the values to the right place. So then the reducers get run, and what you get out of it is something which looks like this: fox, comma 2, brown, comma 2, and so on. So this is sort of a logical diagram of what you expect to happen. How does this happen physically? What are the exact things that run, right? So physically what happens is that there's a daemon, there's a long-running scheduler, which is called as the job tracker, where you can submit a job saying these are my map and reduce functions, right? And this is my input file. Now, this is sort of like the queue subsystem that you've used in the NERSC machines, where you submit a job to it and it'll then run it, right? The only difference here is that the job tracker automatically figures out how many like parts there are. So for example, in this file, we had like 3 parts, which was the quick brown fox, and the second one and the third one. And it automatically creates tasks to run on each of these parts, right? So if, for example, the file size increases, you don't need to change a single line of your code. The framework will automatically distribute it across like more tasks, right? The other thing it does is that it co-locates these tasks with where these files are. This is sort of important when you're reading data from disk. You want to be actually close to or like on the same machine as where the data is stored, because otherwise the latencies are really high. And so this locality is an important factor in like scheduling these tasks. And once you've got these tasks scheduled, it runs it and also saves the output and comes back to you. So it's sort of this submission model where you can submit a job, and after the output is there, you can get a result and like view the result on your screen. So we talked a lot about failures. We saw that there were many causes for failure and that it occurs due to many reasons. How does this thing handle failures, right? So I'm going to go through 3 stages of failure and sort of look at how they get handled. The first stage is what happens if a task fails, right? Like there's a segmentation fault, or like there's some problem with your program and like the task crashes. So what the framework assumes is that your code is deterministic, that you can actually rerun the code on the same data set and it'll return the same answers, right? So it launches the same task on another machine because maybe there was something in the environment, there was something in the software stack that was a problem. And if that also repeatedly keeps failing, it fails the job. It sort of like gives up after a few attempts. This one was a simple one. What happens if your entire node goes down, right? Let's say the machine fails because its hard drive died, its power supply died, or one of the many reasons that we saw before. This is a little bit more tricky because there could have been multiple tasks running on the same machine. So the framework automatically tracks what are these tasks running on these machines, and it automatically reschedules them to run in other machines that are available on the cluster, right? This is a pretty cool feature. So if you're running a large cluster with like hundreds of machines, a machine goes down, doesn't affect you. Still, your job completes and you get back your results. You can call somebody in IT or something to get the machine back up, but your work doesn't get disturbed. And so it's a very important thing, right? And the last part is, what happens if a machine is really slow? This happens due to things like your disk is not completely dead yet, but it's sort of faulty. It has a bunch of sector errors or something like that. And so the computation like proceeds really slowly sometimes, right? And when you especially have tens of thousands of disks, there is some disk which is exhibiting this behavior, right? So in that case, what the framework does is that it launches multiple copies of the same task, right? So for example, in this case, let's say the first machine was bad due to some reason, right? What would happen is that it would make a replica, and it will launch the task in another node to process the same input data. And whichever one finishes first, it will just take that output, and it'll discard the rest, right? This is a really simple strategy of like picking the first among like multiple replicas, but it's very effective. There have been a bunch of papers which have like studied how much benefits this gives, and it's pretty significant and gets rid of most of like the problems which happen, right? So these were like the 3 stages of fault recovery, and stragglers. Such tasks which go really slowly are called stragglers usually. And the MapReduce framework automatically handles these things for the user. So word count was like a really trivial example. Everybody really talks about this. But the model is actually very powerful. People have written a large number of applications which are based on this model. I'm going to talk about a couple of more of them. The first thing is you can do things like search, or for example, grep, where you want to find something in a really large file. But let's say it doesn't fit on your machine, right? And you want to do this in a distributed fashion. It fits really well in the MapReduce model. So the map task here is like you're given a line, and you check whether it matches the pattern that you have. And if it does, then you output the entire line. Okay, that's your intermediate data. And the reducer is an identity function, or just like it doesn't do anything. It just gives the same input as its output. So what you've just done here is you just filtered lines which match your pattern, right? And this is a very nice mapping from what you wanted to do to the MapReduce model. The other example is building an inverted index. This is an application that search engines use. So for example, if you have web documents like hamlet.txt and twelfthnight.txt, you want to build an inverted index so that you can answer queries, right? So if somebody gives you a query with the word greatness, you want to figure out which all pages contain the word greatness, right? So you try to build this inverted index which goes from words to text files or like HTML files, right? And to build this, you can use a MapReduce job to do it. So how would you do that? The way to do that would be your input, you assume, is a bunch of files, each containing some text. And for every word in the file, you output word, comma, file name, right? That's your intermediate data. And the reducer in this case is you get a bunch of file names, and you just want to keep the unique list of file names. So if a word appears twice in the same file, you want to keep the file name once. That's what the reduce function is doing. So if you map this back to what we wanted to do, you have something like for every word, you output the file name associated with it, and then the reducer just merges these things up, and you get an inverted index. So this maps to like the original motivation behind the MapReduce paper, which was you wanted to build this giant inverted index to do web search efficiently, right? So, so just to summarize what we saw in this section, we saw the difference of like what a high-level data parallel model looks like and how it contrasts to like an MPI-based like message passing parallel process model. One of the things is that you get a lot more fine-grained control when you do something like MPI. You can pick which processor talks to which other processor. You can measure the number of like send and receive calls that happen and like how many bytes are sent and so on. You get much lesser control in like this sort of higher level framework, right? But on the flip side, you get things like automatic locality of tasks, and like it handles data transfers for you. You don't need to worry about things like that. So in some sense, the focus of the applications that you use for MPI are more on high performance because you want more fine-grained control and you want to like figure out how to do it, while the focus on these MapReduce models are more about programmability and fault tolerance, like ease of use and how do you deal with failures when you're doing that, right? So this seems like, again, a success story, and you're like, are we done here? I mean, because MapReduce is cool and we probably can call it quits. Well, it turns out it's not quite simple as that, because when an abstraction is really good, what people try to do is that they try to compose it. So for example, you have some input data here, you run a first MapReduce to do something on it, and then you run another MapReduce to do something on it, and so on and so forth, right? And the reason, and this is not a theoretical thing, at a large number of companies, people have seen that most of their real life like examples that they have, be it things like an indexing pipeline or these analytics queries that you have with the help of database like queries, they're usually like multiple steps of MapReduce involved. Sometimes in the order of tens or 20, and sometimes like 2 or 5 steps, right? And this is especially true for things like machine learning algorithms, which want to do iterative steps, right? So in that case, for example, PageRank, if you're computing it iteratively, there are tens or like hundreds of steps of MapReduce that you want to call, right? That doesn't seem like a bad thing, except that you sort of run into problems when you try to do this repeatedly. And there are 2 main challenges that you run into. The first thing is programmability. And by programmability, what I mean is that one of the reasons we picked these high-level data parallel models was that they were easy to write code in, right? But if you want to write this like 20, 30 times over and over again, the whole code base becomes a mess. You have no idea what's coming after another one. You have no type safety. And there's like a lot of boilerplate code. Like this is my mapper, this is my reducer 1, this is mapper 2, reducer 2, and so on, right? It becomes a huge mess. The second problem is performance. So what we saw with the MapReduce model was that our input was on disk. We did some computation, and we wrote it back to disk, right? It's safe because you don't lose data at that point. But it's really expensive because you're bound by the disk bandwidth and latencies that you get, right? It's sort of really hard to do that if you want to do interactive stuff, right? Let's say you're at a console, you're waiting for some output. It's going to take too long. And this is especially true for these iterative algorithms like PageRank or data mining, where you just want to look at your data set and do something about it. So people in the community realize these problems. There have been a lot of efforts to like sort of address this. And today I'm going to talk about one in particular, which is this project called Spark. So just for some history, Spark was a project that started off as a research project at Berkeley in the RAD lab and what later became the AMP lab. And today it's like been commercialized, and it's used in a large number of places and has a large number of contributors to it. So what was sort of the major features of Spark, right? So what Spark said was that we want to retain the good properties of MapReduce, which is things like handling fault tolerance and like doing all these things automatically. But the key differences was that it said, let's have a very clean API and a very functional API, which lets you reduce the number of lines of code that you need to write, right? Let's remove all the boilerplate around and so on. And the other big thing, goal was that we wanted to compose these like pipelines of stages together. Let's optimize those pipelines as far as possible, right? These were two of the big goals behind like the whole effort. And how does it do this? So just to give you a high-level example, this is the word count that we saw. This is the lines of code to do it in the original Google paper, like from 2004, right? What Spark did was reduce that to something like this, to 3 lines of code. No? So this is pretty awesome, right? I mean, you can type this out, you can edit it, you can do cool things with it. And the high-level idea here is that you can chain a large number of operations together. So we're going to look at it in more detail on how we pull this off. And this idea helps us like make it a lot more concise. So before we dig into the details, how useful is Spark? Like, why should we even bother about it? These are some numbers from the research papers published on Spark. And it shows like for applications which are iterative, like k-means clustering or logistic regression, you get almost 2 orders of magnitude improvement, right? Compared to like what Hadoop MapReduce was doing. And we're going to now dig in to see why this is the case, right? How do we get these 2 orders of magnitude improvement? So there are two main aspects to Spark. The first is this idea of resilient distributed data sets, or RDDs. They're just a really fancy term. It's kind of hard to wrap your head around them the first time you see it. But what they are is basically a distributed collection. I guess most of you have used programming languages like Python or something where you have a list API, let's say, right? So just imagine this as a big distributed list which is spread over a large number of machines, right? So what the Spark API does is it gives you a large number of functions that you can run on this distributed list. So it says you can apply a map function on this distributed list, or you can do a reduce on the distributed list, and so on. The nice properties about these RDDs are that they're immutable. So once you create them, they don't change. This immutability helps improve performance in a lot of cases. And the immutability also helps the fact that you can cache these things in memory. So you can have an RDD which is either on disk or on memory, and you can program towards it in the same way, right? This is what's going to help us in our iterative algorithms. So there are 2 kinds of operations on RDDs which are defined. So one are transformations, where you go from one RDD to another. So your input is a list and your output is a list. Let's say you increment every value in a list, right? Your input is a list and the output is also a list. And then there are actions. And by actions, it means things which actually reduce the amount of distributed state to something that you can like save or something you can see on your console, right? Let's say I find the length of a list, right? What I'm doing is I'm doing an action on the list to sort of reduce it to an integer, right? Those are what are called actions. So we're going to look in more detail about what are the transformations and actions in an RDD. So to do that, let's take an example. Log mining is this problem where you have a bunch of things which generate logs, like HTTP servers, any other like daemons that you run. They all spit out a lot of logs, like even your operating system, right? It spits out a bunch of logs. And the question is, you want to interactively search these logs. Let's say you want to find out how many errors there were, or like what were the errors, at what time did they occur, and so on, right? And to do that, we're going to do this in a distributed setting because we have tons of log data, like at Facebook or something. And the way this is set up is you're writing code from a console, a Python console, or let's say a Scala console, right? And this is what's called a driver in this figure. This is where the program is sort of driven from. And then there are these worker nodes which are actually executing the program, right? These are sort of similar to the map tasks that we saw in the previous case. So the way the flow works is in your driver you can issue higher level commands, like saying spark.text file hdfs:/ something. So what this tells Spark is that I want to read this text file, and I want to create an RDD called lines as a result of it, right? So you're sort of taking an input and creating an RDD from it. So this is sort of like the base RDD in this computation. And then if you want to just look at the errors in the text file, what you can do is you can do something like lines.filter, and you get a line inside this lambda function out here, and you filter all lines which start with error, right? So this is a transformation in which you go from one RDD to another RDD, right? The input RDD was all the lines in the file, while the lines RDD was just the lines which had the word error in it. Is that a question? Okay. So what happens next? So let's say you want to actually figure out what were the messages associated with the errors, right? So you can do things like, I want to take all of the errors, and I want to split the errors line that you have by tabs out here /t, and pick the second element that you get, right? So you sort of can like extract the messages that you want. And finally, you can say things like messages.cache. What this means is that once the RDD is computed, it'll actually be saved in memory in all of these machines, right? So what's the point of doing this? So let's say we want to see all the messages, how many messages contain the word foo in it, right? So we write messages.filter contains foo, and we count that, right? Which is sort of finding the length of the list. So this computes some value, and because this is an action, we actually have to like implement this on the cluster, execute this on the cluster. So the driver goes around, it talks to all of the workers and launches these tasks for you. The blocks are read from disk, or HDFS in this case, which is just a distributed file system. And these blocks are used to perform the actual computation. And the actual computation is it looks for lines with error, splits them, and again looks for messages with foo, right? So it computes the results and sends it back to the driver. And the result in this case is a number, which is the count of how many messages there were. While this has happened, the workers also do this thing where they cache the messages RDD in their in-memory store that they have. This is because we explicitly asked like the messages to be cached. So why would we do this? This is because let's say you want to figure out how many messages have another word, let's say bar in it. Then if you do messages.filter contains bar, you actually don't need to go to disk again. You just use the RDD which is in memory, and you process them, and you get a result back to the driver. So the second query runs much, much more faster than the first query. Right? So what this, the higher level implication of this is that let's say you're doing full text search of Wikipedia, right? I give you a dump of the entire Wikipedia repository. You can do this in less than 1 second if you have like 20 machines in your cluster, right? Because you're using the memory of all of these machines to cache part of the data. So also if you have like, let's say a terabyte of data set, to scan it from in memory, it takes 5 to 7 seconds, versus it's like 170 seconds if you want to read it from disk, right? So this automatically gives you this like orders of magnitude improvement over what we were doing before. So the key insight here is that we have a simple programming model which is defined on these collections, and we're also able to exploit the in-memory computations when we need them by using these cache commands. So one of the biggest challenges we said was to do fault recovery in such systems. So how does the system like Spark do fault recovery? Because I just described to you things which are in cache, and what if my cache gets blown away, or what if my machine fails, right? What are we going to do? So the way Spark handles it is that it sort of tracks all of the operations that you're doing, and it remembers them. So it builds what's called a lineage of operations. And whenever there's a failure, it uses this lineage to recompute whatever failed, right? So for example, in this case, we had an input file, which was an HDFS file. We did a filter operation for contains error. We got a filtered RDD. And we then did a map to do the split operation where we got a mapped RDD, right? And now this chain of operations that you see here is what's called a lineage, right? So what Spark does is that it remembers that you did these 3 operations. So let's say a machine fails, whichever had our cache block in it. Next time you go to access it, Spark will recompute this on another machine because it remembers what are the operations that you did to compute it. Right? So this means that you only pay the cost of recomputing what you lost. So instead of saving everything to disk or saving everything on multiple machines, you're sort of remembering what did you do to actually get there and only recompute when you lose things. Right? So this is very efficient use of resources for getting like fault tolerance out of the system. I was going to do a demo, but I couldn't use my computer today to do the presentation, so I'm going to skip this part. But I'll give you a bunch of other links where you can try out Spark and see how it works for you. Instead, what I'm going to do is I'm going to walk through these examples in a little bit more detail. And I'm going to walk through these machine learning algorithms, especially to show some of the features of Spark in greater detail. So one of like commonly used machine learning algorithms is this algorithm of logistic regression, where you're trying to separate out data. Right? For example, you have a bunch of emails and you want to classify them spam, not spam. Right? So you want to figure out which of these emails are spam, which are not spam. Right? So the way to do that is you have some dimension space and you have all these points there, and you want to find a plane which separates out spam messages and not spam messages. Right? It's a kind of a hard problem. You need to like train your model to do this. Right? And a widely used training method is this method of gradient descent, where you start from a random line separating a bunch of points that you have, and you iteratively improve how good this line is as a thing that splits the points up. Right? So you compute what is its distance from the existing set of training data that you know. So you have some messages already marked as spam and like not spam. And you keep improving this model until you get to a place where you minimize how many mistakes you're making for the training data you have. Right? So this is an iterative algorithm which is operating on data sets, and you in each iteration you change what the model looks like. Right? So it's a very good fit for something like Spark. So how does this look like when you write it in Spark? So how this looks like is that you have a bunch of data that you read in, which is again we're using the text file, and we convert it to points and we cache it. This cache is very crucial here because we're going to use this data multiple times in each iteration. Right? And then we start with a random vector, which is this variable w. This is, by the way, Scala code, but you can do this in Python or Java or any other language. You know. And then what we do is we run this for loop for a number of iterations till we converge on the right model for our data set. And in each iteration, we do a map on the data to actually figure out the gradient. Right? So we do this in a distributed fashion. So if your data is split into 10 parts, we compute the gradient in each of the parts, and then we add them up using a reduce function, which is just summing up the gradients. Right? And then we change our weight vector based on how the gradients look like in the previous iteration. So this works. This looks really concise and a nice way to express the algorithm. That's one part of it. The other part is that Spark automatically makes sure it captures all the variables you use and ship it to the cluster. So what do I mean by that? What I mean is that we earlier saw this diagram which showed drivers and workers, right? Like different machines which were involved in the computation. So this vector W is created on the driver, which is your local machine where you're writing code, right? This is the machine where you're operating from. So when you need to run a task on a remote machine, you don't need to do anything special to move this data out there. Spark automatically looks at what are the variables you're using, and it sort of captures all of them when it creates a task and sends it out. Right? This is super useful because it simplifies your programming a lot. Right? So you can just use them like you write normal code, except this is operating in a distributed setting. This kind of iterative algorithm, like I said before, performs really well when compared to systems like Hadoop. And just another performance graph from the research paper, the Hadoop task takes around 110 seconds to run one iteration of logistic regression. Right? On the x-axis, we are varying the number of iterations that we have. And as you can see, Spark in its first iteration takes around like 80 seconds. But since we cache the data in memory from that point, all other iterations take 1 second. Right? So what this means is when you run exactly one iteration, the performance is pretty comparable. 110 versus 80 isn't much. But as you keep increasing the number of iterations, you get much more benefit from like this caching that we're doing in memory. So this is pretty cool. But so far, what we've done is we've only looked at very simple operations, right? Where you have a distributed collection and you're doing a map to get another distributed collection out of it. In some sense, we're not doing anything where we're sharing data across multiple tasks, right? So everybody has their own data set, and they're like processing that in like a sort of a parallel fashion. Spark introduces two different kinds of support for shared variables. Again, keeping in with the theme of the data parallel model, these are simple shared variables. For example, in UPC, we saw these things where you could do a lock, and like you could do an unlock on a shared variable and so on. There's no support for things like that. These are like really simple sharing primitives that are supported. The first one is called broadcast variables, which I'll discuss a little bit of. And accumulators, I won't have time to talk about, but they let you add stuff up, accumulate stuff up across different tasks. So what is the point of doing these broadcast variables? To explain that, let's use an example. So I have the same logistic regression, but I want to do, let's say, a random projection before I do the regression step. And for this random projection, I need this really large matrix, which is, let's say, a few hundred megabytes or something like that, right? You could still do what we were doing before, which is that just use the random projection as a part of your function. Spark will capture it, send it across, and everything will be fine. But this is not efficient. And the reason it's not efficient is that you're taking hundreds of megabytes of data from the driver and sending it to the worker on each iteration of your program, right? So it sort of starts bottlenecking on like this transfer operation that's going on. So the solution is that you have this notion of a broadcast variable that everybody can get access to. Like it's there on all of the workers. And it's sort of cached on all of the workers before the program starts up, right? But the important factor is it's read-only. Like you can't make changes in any worker and expect it to be seen anywhere else. But it's useful in a lot of different use cases like this one, where you can broadcast the matrix before you start, and then you can use the broadcasted variable in your source code, right? And this improves performance by around 3x in experiments which have been done. So this is still a subset of all of the things that Spark can do. The distributed list API that I was telling you about can support a large number of other things, like it can do joins, it can do group bys, and you can do cross products and so on and so forth. And you can also do things like save it to a Hadoop file or save it to a local file and things of that sort. I'll put up links to documentation and things like that at the end, and you can play around with it, but it's very intuitive because you can do it locally as well. Like on a local list, you can do these operations, and this is just a distributed list version of it. So this was all Scala code that I was showing you. Spark is actually just an engine for doing these things. So you can have front ends in any language that you want. There are 3 language front ends other than Scala right now, which are Java, Python, and R. The code kind of looks different in each language based on its own syntax and things of that sort. But the high-level distributed collection API is sort of similar and shared across all of them. It's especially cool to use it from Python because you can use existing libraries like NumPy, SciPy, and things of that sort, and you can use them as a part of your distributed operations very seamlessly, without doing anything hard. And one last slide to talk about the internals of Spark. So far, we've been mostly looking at, as users of Spark, what can we do with it, or what can we get out of it. The internals of Spark are more interesting for explaining why we get performance benefits. So the first bullet point here is about capturing the dependency graph. We sort of talked about this for the lineage, where we're able to replay operations, as it were, to get to handle fault tolerance. So there's a scheduler inside Spark, the job scheduler, which sort of captures this dependency graph as and when you write more operations. There's also this nice property of pipelining functions. This is something I did not touch about when we had the source code up, but the operations in Spark are evaluated lazily. So let's say you say a map or a filter, Spark actually doesn't do anything with it because you've actually not asked anything to be materialized yet. Yeah? So anytime you have an action which says like count or save or something like that, then Spark goes ahead and actually unrolls everything and executes everything. And when it's doing this unrolling, it can like put stages together. It can optimize them so that it runs as few tasks as possible, because each task has some fixed overhead. And this functionality is called pipelining functions into stages. And the last two are basically this notion of locality awareness, which is that Spark knows which disks on which machine have which input, and also where are the memory blocks being stored or cached and so on, so that whenever you launch a computation, it can pick the right set of machines to like assign to tasks. And all of this happens automatically in the background. So from a user's perspective, it's really simple, but there's some good amount of engineering to do that. And finally, we talked a little bit about shuffles when we were doing the word count example. Spark can also cleverly avoid shuffles if it's possible, if it knows that things are partitioned similarly or something like that. So this is a very short talk about the job scheduler. There are a lot more details, and I'd be happy to talk about this offline if you're interested. So Spark itself is a pretty low-level API, though, in considering things that people want to do, in the sense that you need to write out code to actually list out all of the stages, do the filter, map, and so on. Right? There's been this movement of building stuff on top of Spark, in the sense that Spark has an execution engine, and then you give more high-level operations. These are all research projects from the AMP lab. One of the most mature ones is Shark, which is listed at the bottom, which takes SQL queries and decomposes them into these Spark jobs. So you have a console where you can type SQL queries, like select count star from table or something like that. And this also, so one of the nice things about all of these high-level things is they inherit the performance benefits of Spark. So Shark is also orders of magnitude like faster than an equivalent thing done on Hadoop. There have been more recent things which have been libraries added to do graph processing and machine learning. These are all like distributed algorithms which are implemented. So you can open your console and say like pagerank.execute, and PageRank is already implemented for you in a distributed setting. And even things like logistic regression that I showed you, we have a higher level library to do that now. So you can do like logistic regression.train, give you data, and it just trains the model for you. And finally, there's also a streaming API. So far we dealt with fixed inputs of data, like your whole data is available when you start up, right? But there's also this model where data arrives in small chunks. This could be logs, this could be user data, this could be anything like that. And Spark has a nice streaming API to handle these kinds of data sets as well. It's been very successful, this project. We do this thing called the AMP Camp, which is a big data boot camp as a part of the AMP lab. And what we do in this is that there are a bunch of talks, but we also have a lot of hands-on exercises. The last time we did it, this is a photo from that. There were around 250 people who attended this in person, and many thousands were online doing it in parallel. The website is listed here, ampcamp.berkeley.edu. If you're interested in this stuff, you should go and check it out. It's a great introduction to how to use these things, and you can actually walk through each of the steps, and there are like data sets online and like all of the instructions online to use the software. We keep updating it as well. Like we try to do one every year, so we update the material with anything that has changed and so on. Before I conclude my talk, I want to talk about course projects for like CS267 and how cloud computing or these big data tools might be a good fit. The first one is something that I'm very passionate about and I'm actually working on right now, is how do you express linear algebra in these commodity clusters? I guess we're going to see more of this in the rest of the class, where we're going to use MPI to write out a bunch of linear algebra operations. We did matrix multiply. How would you do matrix multiply in a data center, right? And some of the challenges there are dealing with like different topologies or dealing with different like kinds of machines that you have and so on. I also think there's like very good measurement studies that can be done. So I gave a very back of the envelope comparison of EC2 and like Hopper, right? But there are obviously many more details that you can measure and sort of profile and see what works well, where, and why. And the last project idea is this notion that you have these virtual machines, and we were optimizing matrix multiply for like one architecture that we knew very well, like Hopper, right? So if you were to optimize matrix multiply in a virtual machine setting, how would you go about it, right? I actually don't know the answer to that. I have no idea how to do it, but I think it's a good research project to try out. There are many more ideas on things you can do in this setting as compared to the supercomputer setting, and I'd be happy to chat about this as well in case anybody's interested. So in conclusion, what we saw today is that this notion of having large amounts of data, the big data movement, sort of necessitated the commodity cluster and the cloud computing movement that came along with it. The key challenges in this setting is that we use commodity hardware and large scale, so you have a lot of faults, you have stragglers, and you have to deal with it at the software layer. So these data parallel models like MapReduce and Spark, they've sort of been very successful in giving a very simple programming model and abstracting away all of the hard parts from the programmer. So in summary, what I like to say is that the big data and the cloud computing movement has been a reflection of what are the challenges, what are the requirements that have been needed for the applications there, be it in terms of machine learning algorithms or like building computing PageRank or building inverted indices. It's sort of a reflection of the choices that you'll make based on the workloads that you need to run. And that's it. I have 5 minutes more so I can take questions. Thank you.
Question about Spark.
Mm-hmm.
How widespread is the use right now? And also a second question is, given that there's a lot of immutable structures and it's working with a lot of iterative algorithms, how memory intensive is it versus your traditional sort of MapReduce jobs?
Great question. So the first part of the question was how widespread is it, or how widely used is it? I think there are at least on the order of 10 to 20 companies which are have active contributors and which are trying it out. Primarily big companies which are trying it out include things like Yahoo, who have contributors in a large cluster which is like running Spark. And really recently, like this morning or yesterday, Spark became like a top-level Apache project. It's one of these top-level domains. And there's also been a company started to commercialize support for Spark and development of Spark called Databricks by the folks who developed it. So there's a lot of momentum going on behind it. To answer your second question about mutable data structures, I think the challenge exists in both Spark and MapReduce and like any other these data parallel models that you use. Because fundamentally mutability and so what the fault tolerance schemes are doing is they're checkpointing data, right? They're checkpointing either by caching it or by writing it to disk or one of these things, right? And mutability and checkpointing are sort of at odds with each other. I think Spark is a good enough fit if you can identify portions which will be immutable and cache them, right? And you redo the mutable data whenever you want to. But that is a challenge, and it's sort of a good area of research in the sense that if you have a large number of mutable data structures, how do you still make it distributed and fault tolerant? Yeah. Okay, thank you.